So it's maybe about like 4 to 6 times faster than a PC, roughly. And one thing that we did last year was we took a huge word list and kind of created a rainbow table. It's salted by the SSID, but we took the top 1,000,000 words and the top 1,000 SSIDs and created this huge table, thanks to RenderMan. And finally, we have this 40 gig, whole thing of pre-computed values up, and we should have it up.
We have them available if anybody's got an exorbitant large amount of space available on a laptop.
Cool. Okay. Yeah. So talk to RenderMan if you want to get the 40 gigs, or you can grab them off of BitTorrent, thanks to the Shmoo group. And I don't think that they're actually posted on their page right now, but if you do a torrent search, you should be able to find them, according to Hulton. So here's a demo of Cowpatty with FPGA support and some Perl scripts to glue it together. Oops. Oh, what did I do? Check. Come on. Oh no, did I lose my screen? Oh, wait, there we go. Okay, sweet. Oh no. Okay. Oh, here we go. Okay, resize some of these. So all this stuff runs under Windows now. If you want to actually run Cowpatty under Windows, you can grab these binaries if you want. And this actually works with both of our cards, with like our E12 or E16 or whatever. Oh man. Here, I'll show you it without FPGA support. So that's kind of the usage for just running it normally. Right now it's chugging away really slow here. And so actually, I'll go over here and do it at the same time with one of the Pico cards here. I've got this handy batch script here. So that's it running on the FPGA on the right and running on my computer on the left. And this is actually an Intel Core 2 Duo, like about 2 gigahertz or so. So it already found it and went through 4,000 keys, and this one's still on 1,800 or so. So it's obviously a little bit faster. Oh, yeah. There we go. Okay. Now, how are we doing on time here? 5 minutes till Q&A. Okay. Next thing I'm going to talk about is File Vault. How many people use File Vault on Mac OS? Yeah? Yeah, a few people. Okay. So Apple has this cool explanation of File Vault. Secures all your data by encrypting it with 128-bit encryption. This high-performance algorithm automatically encrypts and decrypts in real time, so you don't even know what's happening. The only problem is that we wanted to know what was happening. So essentially, it takes your home directory, stores it in a DMG file, and they basically embed the crypto stuff into the drivers, and it automatically mounts it and does all of the encryption and decryption on the fly from this DMG image. And there's a couple different versions of it. You can read the source, and I think that we've got some more presentations that go in more depth, but do some research if you want to learn more about it. So the cool thing is that it actually uses PBKDF2 for the password hashing. So it was really simple to port over my WPA stuff. I was actually at the CCC and managed to get everything ported over in like 24 hours from the time that somebody told me that it used PBKDF2. We presented on it the next day. But yeah, it's pretty simple. It just uses 1,000 iterations instead of 4,000. And I worked with Jacob Applebaum and Ralph Philip Weinman on doing all this stuff. So yeah, they ended up throwing together this program called VF Decrypt. We called it Vile Fault because we didn't want to have any sort of copyright problems with Apple. So I hope that they appreciate that we took that into account. They actually didn't want to write a File Vault cracker, so they wrote this program that just decrypts File Vault images that are encrypted. And so as long as you have the right passphrase, you can feed it into this program and it spits out a clean DMG with no encryption. But how do you find out the passphrase, right? So I just modified their source and hooked it up to one of our Pico cards. And so this thing will actually take a word list, run it through and find the right passphrase for for your file vault image. And some other attacks that we figured out is they actually don't specify that the memory shouldn't be swapped out to disk. And so if you can somehow use up a bunch of memory in the person's PC, they should swap it out to disk, and you can read it from there. There's also hibernation problems. A hibernation file will contain, their passphrase and their key and stuff. And possibly with ring, you might be able to read it. The weakest link, though, it turns out that the RSA key that they use for the version 2 header actually is easier to crack than the 128-bit key. And also, the salted SHA-1 password that you use for your login is the same password that they use for the file vault image. So you probably want to just fire up their password file into John the Ripper if you have access to that, because then you can use the same password for decrypting their image. So here's some performance comparisons. It's pretty similar to attacking WPA. Top-of-line machine will get about 180 to 200 per second. On one of our FPGAs, it's about 2,000 per second or so. So here's the demo. Let's see if I can get this right. Okay. And this you can also run without an FPGA if you like. Oh yeah, here. So I've got this batch script here. You just give it a dictionary file in the DMG image, and so this is it running without an FPGA. And this is it running with the FPGA on my laptop. So there, found the passphrase. Cancel that. Okay. Now, the last thing I'm going to talk about is Bluetooth pin cracking. There have been a couple other people that have done stuff like this. There's these people that wrote a paper on it that you can download off the internet. Just Google for it. And also, another person, Thierry Zoller, wrote his own implementation of this. So you can use mine, or you can use a bunch of other implementations. Essentially, Bluetooth uses the Safer Plus algorithm and uses it for pretty much all the things they do. And so basically the exchange, it's very similar to WPA in that you have a bunch of data that goes across the internet to exchange keys and verify that everybody has the right key. But the only thing that you don't really have is a pin. And because the pins are actually just numerical digits most of the time, it's a really small amount of key space that you have to search. The maximum is basically 10 to the 16, which is still fairly small. And most people don't actually use the characters, and most people will use like either 4 digits or 8 digits. So I basically implemented Safer Plus and then wrapped around the stuff around that to implement their other specific algorithms that are used for the key exchange. And this is essentially the pseudocode for doing the whole thing. You can look at it more later. But but here's all the values, and we're just brute forcing the pin here. Is that for me? No. Oh, okay, all right. So essentially, one safer algorithm here, and then I just loop the output into the input and start swapping out these different algorithms and just basically muxing the whole algorithm. And the pin generator is done on the FPGA, so it keeps it really fast. And once it actually finds a pin, it just says, okay, this pin matches, so it backs it up and figures out, okay, that's the correct pin for the whole thing. This is actually super fast. On a normal PC, it does about 40,000 per second, which means for a 4-digit pin, 1/4 of a second. It takes about 42 minutes for an 8-digit pin. One of our cards, we can do about 10 to 15 million per second, which is a few hundred times faster. And an 8-digit pin only takes about 10 seconds. And I'll show you this in a minute. After this, I'll pretty much be done.
I'm going to get uncomfortably close to you until you stop.
Okay, all right.
There's also a bug that's up here.
Oh, sweet. Is that a prize for somebody asked a good question? Okay, so this is cracking one of these capture files that I have on my PC here, and so this script is supposed to go through 6 different captures that I have, with some that are like 5 or 6 digits long, some that are 8 digits long, and so this is it running on the FPGA. Wait. Huh. Why isn't it working?
I don't want to go to the next step.
Okay, let me pop the sound pop back in. See if that works. Okay, there we go. The first one, it cracked in a split second. This next one is an 8-digit one. It cracked in a split second. And there we go. It cracked all 6 of these in about a total of 5 seconds. And the other one, it'll probably take about a few hours. So there you go. And I'm just going to skim through here real quick.
What? No.
No? Okay. Wait. Go into the conclusions here. There we go. Okay, questions? Anybody?
What the hell just happened?
Okay, so our compact flash ones, we just came out with our newer Express card ones. So the compact flash ones we're discounting to around $2,000. If you want, we're doing a show special for about $1,900. $1,800. And then for our Express card one, it's going to be around $19,000 to $2,000 or something like that. So.
Have you considered the manufacturer of ICs based on FPGA designs to sell them at a lower cost?
Manufacturers of ICs?
You're modeling an IC with your FPGA. That's what you're burning the fuses.
Yeah.
Consider actually producing ICs off of those?
If you can find enough people that want them, we could probably do that. Yeah, but you wouldn't be able to swap around, what programs you're using with it. Oh, okay, sorry.
It still doesn't do it.
Yeah. Well, yeah.
Yay, let's hear it for Hikari. Yeah. So he is about the most understated individual I think I know that gives these kind of talks, because he'll be up here and be like, this is kind of cool. And boom! Here's this thing that's 100 times faster. You're like, is that really? Oh my God, it is 100 times. No one else is kind of reacting though, so I'll just sit here and watch him quietly. It's like, my Lord, I've been in a couple conferences where we did that GS